Hi, Andrea here. In the last few videos we talked about natural numbers and their operations, addition and multiplication. With this in our hand, we can introduce the notion of ordering. What does it mean to order natural numbers? Well, it means that a natural number comes before or after another one. Such concept can be visualized considering addition and successor. A natural number m comes before another natural number n if we need to count forward a certain number of times to go from m to n. In other words, m is smaller than n or n is bigger than m. We write it down in the following way. As we know, such concept of counting forward is linked to addition. In fact, if we need to count forward for a times to go from m to m, we say that n is equal to m plus a. Last but not least, it is possible to indicate that a number can be smaller than or equal to another. We can write m is less or equal than n. Also, the other case of n is greater or equal to m can be written as well, indicating that n can be also equal to m. Fantastic! However, now the interesting part. We can explore the relation less than and greater than we have just defined. Let's take three natural numbers n, m and k. We are going to prove some properties of the order for natural numbers. The first one is called transitivity of order. It tells us if n is greater or equal to m and m is greater or equal to k, then n is greater or equal to k. Let's prove that using the basic definition of greater equal. The relation n greater or equal to m can be written as n equals to m plus b. In the same way, m is equal to k plus a. Now let's take the first equality and let's write it using the expression of m. We get n equals k plus a plus b. By the associative property of addition, we can write n is equal to k plus a plus b. We can simply call the sum of a and b as c, obtaining n is equal to k plus c. This expression is the exact definition of n greater or equal to k. Now, a second property to prove, known as symmetry of order, is the following. If n is greater than or equal to m and m is greater than or equal to n, then n is equal to m. The two starting inequalities tell us that n is equal to m plus b and m is equal to n plus a. We can substitute again m in the first equality with its expression, so n is equal to n plus a plus b. The only way the last relation can be true is with a equal to 0 and b equal to 0. Using these values for a and b in the starting expressions, we get n equals m. Finally, the third one. Addition preserves order. N is greater than or equal to m if and only if n plus k is greater than or equal to m plus k. The if and only if part means that we can prove the first relation using the second one, but also the second relation using the first one. It is kind of a double proof. Let's start proving that if n is greater than or equal to m, then n plus k is greater than or equal to m plus k. So, the green part. Again, let's write the first inequality as n equal to m plus a. If we add k on both sides, we get n plus k is equal to m plus a plus k. Thanks to the properties of addition, we can write it as n plus k equals m plus k plus a. The expression in the parentheses can be seen as a simple natural numbers. Therefore, the relation has the form that we know is linked to an inequality. We can say that m plus k is greater than or equal to m plus k. Now, the opposite path. If the second relation in red is the starting point, we can write n plus k is equal to m plus k plus a. This is the same relation than before. We can simply make the same steps backwards and we are done. That's really nice. Now we are more familiar with inequalities. To conclude, we cite a property of multiplication linked to this topic. Multiplication preserves order. If n is greater than or equal to m, then k times n is greater than or equal to k times m. I promise this is the last time we write the starting inequality as n equal to m plus a. What happens if we multiply both sides by k? We can write k times n is equal to k times m plus a. By the distributive property of multiplication, it becomes k times n is equal to k times m plus k times a. The last term, k times a, is just another number, and we can call it b. Therefore, we end up with k times n equals k times m plus b, and this means that k times n is greater than or equal to k times m. Now, ordering allows us to represent natural numbers in a new way. We start from 0, then 1 is greater than 0, then 2 is greater than 1, and so on. This means our numbers are along a line. Such line is simply called the number line. Super! Now we are done with the natural numbers, and you have now the basics for the rest of mathematics. Good job!